Hello everybody, Hod Lipson here. I want to talk about a paper we just published about discovering variables in data. So what does that mean? So a while ago we published, maybe almost a decade ago, we published a paper on how we can, using AI, go from data directly to an equation. So we recorded the motion of a double pendulum. We extracted the angle and angular velocity of the two arms, the four variables, and automatically we went from those variables to discover equations that describe those dynamics. So it was a very interesting paper, very powerful tool, and that tool, that equation extractor, if you like, belongs to a long history of lots of different software tools that try to do that. Started with Pat Langley's work with Bacon back in the 70s, through John Koza's work in the 90s, our own work back in 2007 on recovering dynamical systems, and more recent work by Steve Brunton and Nathan Kutz about with Cindy and AI Feynman at MIT with Max Tegmark and lots of other processes and software tools. But all of these tools go from variables to the equation. In other words, they do step two. They go from, in this case, the angular velocity of a swinging pendulum or any dynamical system to the equations. But the first step of observing a dynamical system and extracting what the relevant variables are, that has somehow resisted automation. We still do that manually. That's what scientists do. They observe phenomena, they rub their chin and scratch their heads, and they come up with the variables. And once we have those variables, we can start using all these wonderful AI tools to extract the equation automatically. So what we did in this paper that we just published is look at that very difficult first stage, which is looking at some physical process using a camera or some very generic observation tool, taking that huge amount of data and trying to extract what are the variables that describe that phenomenon. So let me walk you through what that means. So what we did in this paper, we took a very generic dynamical system. Actually, we took quite a few, but I'll demonstrate this with this classical double pendulum. So double pendulum, again, if you're not familiar with it, is a crazy contraption of a pendulum hanging off of another pendulum, and it swings wildly. So you can see on the left there what the real physical double pendulum does. This is a video recording, and we took basically a deep learning system, and we had it look at a sequence of frames and try to predict what the future frames of that video are going to do. So we trained the system to do that, and eventually, after doing this for quite a while, we got the AI system to be able to predict what the video is going to look like. So obviously it understands, quote unquote, something about the dynamics. But now the question is, can we extract what the variables are from that a big AI systems that is doing the prediction? And we said let's start with just figuring out how many variables are needed to depict to describe this double pendulum. So we know the answer is four. But let's see if the AI system can figure that on its own. So again, we trained the AI system to go from a sequence of frames all the way to the future frames, and we go through we throttle it through a latent space. And the question is, how tight can we squeeze that latent space in the middle such that the predictions are still good? Now, we can squeeze it more and more. There's a lot of details on how you actually do that. It's pretty tricky, but once you do that, we found that the answer is 4. It's about 4.7 to be exact. There's details on how exactly you get that number from the data, but what we found is that you can squeeze it all the way to 4.7. That's interesting because we know that the ground truth for the double pendulum is 4. In other words, the system figured out that there are about 4 variables that are describing this dynamical system. Great. So that's a system for which we know the answer. What happens if we take a dynamical system for which we don't know the answer? So here's an example of a loop of fire in the fireplace. We look at this. We have the system examine it for a long time. make its predictions. Again, the predictions in themselves are only a means to extract the variables, right? So we're not interested specifically in the predictions, although they're nice to look at. It's quite amazing to me that it can predict what the fire is going to do about half a second in advance. But when we actually look at how far we can squeeze it, the answer is 24. So in other words, there are about 24 state variables that are needed to describe the dynamics of this particular fire flames that you see. So we did that for 9 different dynamical systems: the fire, a lava lamp, elastic double pendulum, stick swing dynamical system, all kinds of things. Some of them we know the answer, and some of them we don't. And we saw that for those that we know the answer, it found it pretty closely. And again, for those that we don't know the answer, we can only look at this and say, okay, this looks reasonable. It sounds reasonable that a fire is slightly more complex than a lava lamp and an air dancer and so on. But we don't know the ground truth. But it's interesting to explore this. All right. So the next question is, what do these variables mean? All right. So we know how many variables. The system can actually extract the variables. Now we want to know what the variables are. We want to actually plot them. Now, the reality is that we're stuck at this point. We don't know what the variables actually are. The system gives us the variable, but doesn't give us any kind of description in words. So it's not explaining what the variables are. It's just giving us 4 variables for the double pendulum. So are the variables, do they match the angular and angular velocity that we usually use in physics? Well, the answer is no. These variables don't match the traditional way of describing a double pendulum. There's some other way of describing it. We haven't figured out yet how the AI is analyzing what variables it's using. We just know it's found 4 variables and they are not what we used to. So it's a little bit of an enigma. But when we plot these variables against each other, we can see some very interesting dynamics. We get these beautiful pictures that show how these variables affect each other and how they change over time. So we know they're descriptive and we know they're useful. The videos that it predicts are correct in almost any way you want to measure it. So it's doing the right thing. We just don't know what they mean. So let me step back and tell you why I think this is all important. Historically, if you look at the way science has evolved over the centuries, you have all these famous figures that come up with equation, and we celebrate these equations like Newton discovering F equal ma back in the 1600s. But what we don't realize that a far greater achievement than just finding the equation is actually discovering the variables. Somehow Newton figured out a concept called acceleration. Before he did that, nobody actually thought about this idea of acceleration, but he did. And by doing so, once he figured out those variables, he could start formalizing a relationship. Einstein formulated a relationship between equivalence between energy and mass. But in order to find this now iconic equation, he had to know about the concepts of energy, mass, and speed of light. He had to know about these concepts. How did he come to know about these variables? That's what we're trying to do here. So if you look historically, all these different models, the scientific models that people create, involve these very important concepts like mass, velocity, acceleration, energy, force. And the reality is that before you can discover any law of physics, you first have to have a concept of the variables. If you don't have the variables, you cannot write the equation. Carnot, who came up with thermodynamics, had to have the concept of pressure, volume, temperature, entropy before having these concepts. There's no way he could come up with laws of thermodynamics. And that's true for Navier-Stokes that have to deal with pressure and viscosity, or Maxwell equations that have to do with magnetism and electric fields. You cannot come up with laws of nature before you understand what the variables are. So if we can have an AI that can look at a system and figure out what the variables are, that's a precursor to any automation in turning these variables into a law or an equation. So that's what we did today. And again, we're stuck with this mystery of what the variables mean, and that's what we're going to work on next. Thank you.